This video will use factorial and double factorial to generate the expansion of the sine function, the Taylor-Maclaurin series expansion. We begin with the dataset of the sine function, which is our formula, sine of the x values from 0 to 8. And we'll chart this. We will use scatter chart. Insert chart. This should be scatter chart. Use row 1 as header, column A as label. And a series. Trend line, polynomial to the 8th degree. Label, use the equation. The legend, position at the bottom. And here is the trend line and the trend line polynomial of the sine function. We will use the Taylor-Maclaurin series sum expansion to generate the same. So which is the summation of a times x to the power 2n plus 1, where a, the coefficient, comes in two forms, the factorial, which is negative 1 to the power n over factorial 2n plus 1. The other one is the double factorial, which is in the form of negative 1 to the power n over double factorial 2n plus 1 times 2 to the power n times factorial n. And the value of n is from 0 to infinity. So we go to infinity. 16 is good enough. So we calculate the coefficient in the double factorial form. So RA formula, minus 1 raised to the power n divided by, denominator has three parts, 2n plus 1 double factorial. So double factorial 2 times n plus 1. The second part, that is 2 to the power n. So 2 raised to the power n. And the third part, times, that's factorial n. So factorial n. And then enter. Next, we continue with the other coefficient using the factorial, which is our formula, minus 1 raised to the power n divided by factorial 2 times n, that's 2n plus 1, so 2 times n plus 1, and enter. These values are exactly the same. Now we can continue with the expansion, which is our formula, series sum of the x values raised to the power 2n plus 1. So the x values raised to the power 2n plus 1, where 2n plus 1 starts from, at n equals 0, 1, followed by 2 times 1, 2, 3. So 1, 3, 5, 7, 9, 11. So that is starting from 1, incremented by 2. And the coefficient, you can choose any of the two. We'll start with the double factorial. And enter. So here you have the expansion, but no polynomial. So we edit the chart and show the trend line, series, trend line, polynomial to the 8th degree, and show the equation as label. And here the polynomials are the same. So we can expand this a little bit bigger. So they're the same. Polynomials are the same. We'll calculate this polynomial regression coefficient using Linus. To do that, we complete the Linus matrix, starting with the power. This is transpose from 0 to 8. And the elements. So array formula of the x values raised to the power 0 to 8. Now we can calculate the Linus polynomial regression coefficient. So Linus data y, that is for the sine x, and dot x, comma dot x. Then the expansion. So Linus data y and comma dot x. And enter. Let's compare. So the coefficient of x to the 0, 0. This is 0. 1.16, negative 1.16 times 10 to the negative 29. That's already 0. The coefficient of x, 1.07. Coefficient of x squared, minus 0.194. Coefficient of x cubed, 0.0433. Coefficient of x to the fourth, negative 0.119. Coefficient of x to the fifth, 0.0474. Coefficient of x to the sixth, that's negative 7.38 times 10 to the minus 3. Coefficient of x to the seventh, 5.14 times 10 to the minus 4. And coefficient of x to the eighth, negative 1.34 times 10 to the minus 5. Suppose we use the factorial. So change this to d. Change this to d and d. So we're interested in the factorial. We use the factorial now. Enter. The coefficients are still the same. The polynomials are still the same. The trend lines are still the same. And the data sets are still the same. So because this is equal to this, the factorial and the double factorial coefficients are the same. This completes the use of double factorial in the Taylor-Maclaurin series of expansion of the sin x, and using also the Linus polynomial